Thank you, David, for this introduction, and thank you for this wonderful opportunity of presenting my thesis research. So my talk is basically divided into two parts. In the first section, I will try to give a broad motivation of why we should study white dwarfs, why they are exciting objects, and how they can be useful to other areas of astronomy. Then in the second section, I will delve more into exactly what I did for my PhD thesis on the atmospheres of cool white dwarfs. So of course, white dwarfs are the final evolutionary stage in the life of the vast majority of stars. So it's a stage that is reached once a star has exhausted all its fuel during the main sequence and red giant phases. So it's this little tiny core that is left behind after the planetary nebula phase. 99% of the mass of a white dwarf is contained within its core, which is usually made of carbon and oxygen. And this core is surrounded by a helium envelope, which makes up about 1% of the white dwarf's mass. And then there's also a thin layer of residual hydrogen, which makes up at most 0.01% of the white dwarf mass. The physical conditions encountered in white dwarf span a wide range of parameters. So at the center, we have very extreme densities, so above 10 to the 6 gram per cubic centimeter, and temperatures of the order of 10 to the 6 Kelvin. So of course, white dwarfs are a very compact object. So we're talking typically about 0.6 solar mass compressed into a volume similar to that of the Earth. At the other extreme, we have the atmosphere. So the atmosphere is usually just a low density ideal gas, but it can also in some cases be closer to liquid densities. As for the temperature of the atmosphere, it ranges from about 10 to the 5 Kelvin for the very hot and young white dwarfs, all the way to 3000 Kelvins for the cool and old white dwarfs. So why should we study white dwarfs? What can we learn from them? Well, I think the first major reason to do research on white dwarf is the potential of white dwarf cosmochronology. So one of the most interesting characteristics of white dwarf is that because they have already exhausted all their nuclear fuel, the only thing that they can do for the rest of their existence is to simply cool down in a monotonic fashion. Because we can model this cooling and because we can measure white dwarf surface temperature from photometric and spectroscopic observation, it means that we can quite easily infer a white dwarf age. In the details, we also need to care about the white dwarf mass because this affects its cooling history, and we also need to care about the white dwarf's atmospheric composition because different atmospheres have different opacities, so this changes the cooling rate. But the important point here is that all those three parameters, so temperature, mass, and atmospheric composition, are parameters that we can measure from comparisons between atmosphere models and spectrometric and photometric observations. So using this technique, you can measure the age of a white dwarf, and then you can add to this age the age of the main sequence progenitor of the white dwarf to get the total stellar age of the white dwarf. So if you do this, you can measure the ages of different stellar populations within our Milky Way. And this is a technique that has been used numerous times in the past. And it's also possible to go even further and not just look at the total age of a stellar population, but to look at its stellar formation history. So we can trace back during the last 10 billion years or so how has the stellar formation rate changed through time. So I cannot stress enough how this is an important property for white dwarfs. For most stars, it's just very difficult to measure ages, mostly because their observable properties change very little over time. So we don't have a good resolution on the age, and we end up with large uncertainties. In contrast with white dwarfs, because we have this continuous cooling, it's much easier to discriminate between different ages, and that's why white dwarfs are so useful for cosmochronology. Now, a second very important thing that we can learn from white dwarf is that they are currently our only observational window onto the bulk composition of exoplanetary objects outside our solar system. So this is a more recent realization, and let me explain you how this can work. So we know that up to 50% of white dwarf show signs of metal pollution in their spectra. So by metal pollution, I mean that we can see in their spectra the signatures of elements heavier than hydrogen or helium. So we can see things like calcium, sodium, magnesium, and iron featured. So at first, this observation was very puzzling because heavy elements are expected to sink very rapidly below a white dwarf's photosphere. So we should not see them. So in the worst cases, those heavy elements should disappear out of our view within a few million years. So it's quite surprising to see them in white dwarfs that are billions of years old. So the solution to this problem is that those heavy elements must have recently arrived into the white dwarf atmosphere. And the most plausible mechanism to explain this delivery of heavy elements is the accretion of rocky planetary debris by the white dwarf. So this scenario goes as follows. So let's say you have a planetary system around a main sequence star. Well, a portion of this planetary system will survive the post-main sequence evolution, such as that when you reach the white dwarf phase, there are still some comets, minor planets, asteroids that are orbiting the white dwarf. Then through time, some of those orbits can be destabilized, and those rocky objects can venture very close to the white dwarfs, where they are torn apart by tidal forces, and they form an accretion disk, and they are eventually accreted onto the white dwarf atmosphere. So this scenario is not only supported by the detection of heavy element lines, there are also many other independent observations that confirm this, such as the detection of accretion disks around white dwarfs. So we know dozens of those, and they can be seen as infrared excesses. And there are also a few cases where we see planetesimals that are transiting in front of the white dwarfs, such as in this example here, where we can see that the light curve is clearly asymmetric, which is indicative of a planetesimal that is in the process of disintegrating. So this is really a smoking gun for this idea that white dwarfs accrete planetary debris. So now what's really exciting about that is that by studying the white dwarf atmosphere using atmosphere models and observed spectra, we can take the photospheric abundances that we determined from this atmospheric analysis and convert them into what was the composition of the original planetesimal that was accreted. It's a bit tricky because we need to account for the fact that different elements don't sink at the same rate in the white dwarf atmosphere. So some will sink more rapidly than others, which means that the abundance ratios that we are observing now in the white dwarf are not necessarily the same as the abundance ratios that characterized the original planetesimal. But this can be taken into account. And by doing so, we can then compare the bulk composition of those rocky bodies to that of known solar system objects. So in most cases, we find that they have a composition very close to that of CI chondrites. So CI chondrites are meteorites with a very primitive composition. So primitive composition in the sense that their composition is close to that of the original solar nebula. So of course, it's not surprising to find that most of those extrasolar rocky bodies have, on average, a composition close to that of the average solar system. But there are also some more exciting cases, such as the detection of accreted planetesimals that show sign of differentiation. So where you have an iron-rich core surrounded by a mantle and a crust, and there's also detection of volatile-rich planetesimals, which is indicative of the accretion of something like a comet. So a little known historic fact is that actually white dwarfs were the first objects to provide us with the observational evidence of the existence of exoplanetary systems. So the evidence came as early as 1917 from the white dwarf Van Manen 2, which is the third closest white dwarf to our sun, and also the third white dwarf to have been discovered. So if you look at the spectrum that was taken then in 1917, we can see two little dips over here, and those two little dips are the ionized calcium H and K lines. So of course it was not known at the time, but now we know that the only way we can explain the presence of calcium in this white dwarf atmosphere is that it must have been recently accreted by the white dwarf from disrupted rocky objects. A third major reason to study white dwarfs is that they are an exceptional laboratory to study extreme physics phenomena that we cannot test in the lab on Earth. So of course the reason for that is that the densities reached in white dwarf cores are very high, and those are densities that we cannot reach in the lab. And under those conditions, there are many interesting dense plasma physics phenomena that are predicted to occur. And what's really cool is that we can use white dwarfs to test our understanding of these dense plasma physics phenomena. So one of those important phenomena is the core crystallization of white dwarfs. So if we look at the core of a young white dwarf, it would look something like this. So it's carbon oxygen plasma, so you have carbon and oxygen ions that are moving all around. But as the white dwarf ages and cools down, the ions become increasingly correlated together, and at some point they are so correlated that they freeze onto a lattice structure. So what happened here is a liquid to solid phase transition. And this is what we refer to as the core crystallization of white dwarfs. So what's really cool is that even though this phenomenon occurs well below the regions that we can see of the white dwarfs, it occurs in the core, there is an observational signature from that. And the observational signature comes from the fact that because it's a phase transition, there is release of latent heat when going from a liquid to a solid plasma. So let me now show you how this observational signature looks like. This signature is visible in the luminosity function of massive white dwarfs. So that's what I'm showing here. So this plot was published just last year in Nature by Tremblay et al. And is based on data from the Gaia satellite. So what the luminosity function is showing is just how many white dwarfs there are per different luminosity bins. So here on the left you have very hot and young white dwarfs, so very luminous. And on the right you have very cool, old, dim white dwarfs. So the first interesting feature of this luminosity function, and that's a feature that has been recognized for decades now, is it's this cutoff that we see at low luminosities. So this cutoff is directly related to the finite age of the galactic disk. So it simply reflects the fact that white dwarfs did not yet have the time to cool down to lower luminosities than this cutoff within the last 10 billion years or so. But now the new exciting feature is this bump that we see here. So if we look at predictions from evolution models, we see that it's exactly where this bump occurs that white dwarf models predict that the cores of white dwarfs should be in the process of crystallizing. So that's what I'm showing here. I'm showing the fraction of the white dwarf's core that is crystallized. So because white dwarfs are in the process of crystallizing when they reach those luminosities, it means that there is a release of latent heat and also release of gravitational energy because there is a redistribution process of the carbon and oxygen ions during the phase transition. So all this release of energy means that the white dwarf cool down more slowly when they reach those luminosities. So what we see here is basically just a traffic jam of white dwarfs. So white dwarfs cool down more slowly when they are in the process of crystallizing. We can try to model this process using white dwarf evolution models and population synthesis simulations. So far, this pileup is always underestimated, and this is likely due to the role played by a third species that is present in white dwarf cores. So there's not only carbon and oxygen, there's also about 1% of neon-22, and the role played by this species is still not that well understood. So to me, what's really interesting here is the interplay between the theory and the observations. So on one hand, we can use our dense plasma simulations to try to better understand those astronomical observations and develop more accurate white dwarf models. And on the other hand, we use those astronomical observations to refine our understanding of dense plasma physics phenomena. So to me, that's a very interesting interplay here between theory and observations. Then I should add that white dwarfs are not just tools to learn about other cool stuff in astronomy and physics, they are also very interesting objects in their own right. So we still have many puzzles to solve with white dwarfs, and here I'm just going to discuss one of those puzzles because I will need to refer to it later on in my talk. So this puzzle concerns the spectral evolution of white dwarfs. So spectral evolution refers to how does the chemical composition of a white dwarf atmosphere changes as it cools down. So it turns out that there are different competing physical mechanisms that can change the composition of a white dwarf atmosphere. So it's not because it starts with a helium-dominated atmosphere that it will stay with a helium-dominated atmosphere all its life. And by looking at how this helium-rich to hydrogen-rich ratio changes as the white dwarf cools down, we can hope to better understand those mechanisms that shape the evolution of white dwarfs. So let's start our journey at very high temperatures, so with very young white dwarfs. So at the beginning, most white dwarfs will have a helium-dominated atmosphere, and this is just because the thin residual hydrogen layer is all mixed up with the helium layer, and there's much more helium than hydrogen, so we see them as helium atmosphere objects. Then at lower temperatures, this picture is completely reversed, and we see much more hydrogen atmosphere objects than helium atmosphere objects. And this reversal is just due to gravitational settling. So basically, there was enough time by the time for hydrogen to float up on top of the helium layer. At lower temperatures, this is partially reversed, and we see helium atmosphere objects reappear. And this is well understood. It's due to convective dilution, where the convection zone of the helium envelope reaches the thin hydrogen layer. So depending on the thickness of the hydrogen layer, you can completely dilute your hydrogen in the thick helium envelope. This process is further increased at lower temperatures, but now it's due to convective mixing, where the convection zones of the hydrogen and helium layer merge together, so you can mix even more objects, so you can mix the hydrogen of even more objects into the helium layer. At lower temperature still, it appears that this process is reversed, at least in part, and unfortunately we don't yet understand why this is the case. We don't know what's the physical mechanism at play here, so this is a puzzle that still needs to be solved. And if we look at even lower temperatures, then it's not even clear what the spectral evolution looks at all. Although I will come back to this question later on in my talk. Okay, so I hope that those examples of applications convince you that white dwarfs are amazing objects, providing us with great opportunities to learn about a lot of stuff, and that they are useful for other areas of both physics and astronomy. Now, what's really important to realize is that all those applications, they depend to a large extent on the use of white dwarf atmosphere models. So the white dwarf atmosphere models are needed to determine the fundamental parameters of white dwarfs, so temperature, mass, and atmospheric composition. If we don't have those parameters, or if they are not accurate, we cannot determine a white dwarf age, and we cannot determine the composition of a planetesimal that they might have accreted. So really, white dwarf atmosphere models are at the root of any applications that involves white dwarf. So the way those models work is that we give as an input the three fundamental parameters, so temperature, composition, and mass. And from that, the atmosphere code can compute an emergent flux. We then compare this synthetic flux to observations, and when we have a good fit, then we can claim that the parameters that we gave as an input are the actual parameters of the white dwarf that we are interested in. But here, it's important to point out that those atmosphere codes also depend on a lot of input physics, so things like convection, equation of state, opacities, radiative transfer, and all this input physics is not always well known. And this is particularly the case for the coolest, oldest white dwarfs, which is a big problem because the coolest, oldest white dwarfs are often the most interesting objects to study given their age. So let's see what's the problem exactly with cold white dwarf atmospheres. So if you look at a warm white dwarf atmosphere, you will have quite a lot of electrons in the atmosphere just because of the Sa ionization equilibrium. And if you have many electrons, it means that the atmosphere is quite opaque. And when you have an opaque atmosphere, the atmosphere is quite puffy. So the region that you're seeing, or in other words, the photosphere, is located at densities that are not too high. On the other hand, if you have a very cool atmosphere, and especially a cool helium-rich atmosphere, then you have much less electrons because of the low temperature, which means less opacity, so the atmosphere is very transparent. And because it is so transparent, the atmosphere will be much more compact, so it will only be several meters thick. So this means that the region that we're seeing in cool white dwarf atmosphere, and especially in cool helium-dominated white dwarf atmosphere, will be located at densities that are quite high, and this is the fundamental challenge with cold white dwarf atmospheres. So let me now show you what conditions exactly we are dealing with. So I've plotted here the density, temperature profiles of the Sun, Jupiter, and the cool white dwarfs. And in each case here, you have a circle that indicates the location of the photosphere. So you can see that when we are modeling a cool white dwarf photosphere, we're modeling something that is much denser than what we're used to with typical stellar atmospheres. And in fact, we're talking about conditions that are more similar to what is found in the inner layers of giant planets. Of course, you might say that, well, looking at the y-axis here, the photosphere is at a density of about 1 gram per cubic centimeter, which is not very extreme. It's true that it's not extreme, but it's high enough to cause a lot of trouble for white dwarf atmosphere models. So the fundamental problem is that stellar atmosphere codes typically heavily rely on the ideal gas approximation, where you neglect interaction between particles, and this is totally fine in most stellar atmospheres, but it's no longer applicable to cool white dwarf atmospheres because the high density implies that you have many body interaction between species, and this affects the opacities, the chemical equilibrium, and the equation of state. So it's really important to take that into account. So if you don't take those non-ideal high density effects into account, here's the kind of problem in which you run into. So I'm showing here 3 examples of cool white dwarfs. So in black you have observed spectra, and in green you have the best fits that we found using what were the state-of-the-art white dwarf atmosphere models just a few years ago. So obviously, when you have such poor fits to the data, you cannot trust the fundamental parameters that you're finding from your fit, which means that all the applications that derive from those parameters are cloaked with uncertainty. So you cannot trust the age that you find for those objects, nor can you trust the planetesimal composition that those objects have accreted. So my job for my PhD was to solve this problem, and to do so, I relied on computational tools that were originally developed mostly for application in condensed matter physics. So those tools are known as first principle methods or ab initio calculations. So the idea behind those methods is to use only the most basic laws of physics to simulate from scratch how would the given system of atoms behave under given temperature and density conditions. So for example, at some point during my thesis, I was interested in modeling the opacity caused by collisions between hydrogen molecules and helium atoms. So to do that, I relied on a method known as density functional theory molecular dynamics, where the idea is that you just place your atoms in a simulation box, and then from this configuration, you can solve an equivalent of Schrödinger's equation to obtain the electronic density around your atoms. And then from this electronic density, you can compute potential, forces, and accelerations, so you can resolve the dynamic of the system and evolve it by a small time step. You can then repeat this process again and again and again until you really have simulated how would this system of atoms have behaved under white dwarf relevant conditions. So this is a very powerful technique. It's also very intuitive to understand because it only relies on some of the most basic laws of physics. But the main drawback here is that it's a quite computationally intensive approach. And that's why it's only recently that this kind of method has become available for the kind of applications that I am interested in here with white dwarfs. So I will now go through those three examples of cool white dwarfs and show you how different building blocks of atmosphere models have been improved by my thesis to better match the observations. So our first example is a white dwarf that has accreted a planetesimal, so that's why we see those ionized calcium lines. And here the problem was obviously that when we were putting enough calcium in the models to fit the ionized calcium lines, the model was also predicting this very strong neutral calcium line, which is just not present in the observation. So the problem here had to do with pressure ionization. So the idea is that if you take, for example, a calcium atom and you place it in a dense medium, the interactions with the surrounding particles can knock off the outermost electron of the calcium atom and transform it into a calcium ion. So this was already taken into account in white dwarf atmosphere models, but it was done using a rather crude hard sphere formalism. So here what I did is that I used ab initio calculations to devise a way of accounting for this phenomenon using only the first principles of physics. So when I did that and I implemented this in atmosphere models, I found that this problem completely disappeared. And to me, this is a very satisfying result because this new implementation of pressure ionization does not depend on any free parameter. So there is no knob that I can tweak here to get the right answer. Everything really comes from the first principle calculations. One might think here that I could also have played with the temperature because the temperature is another way of changing the ionization balance. But actually, in this case, as with all the other examples that I will show, the temperature is independently constrained from a fit to the photometric observation, so from the UV all the way to the infrared. So it's actually not a free parameter in this situation. My second example is another white dwarf that has accreted a planetesimal, so that's why we see all those iron, calcium, magnesium, and sodium features. And here the problem mostly had to do with how pressure broadening of the absorption lines was computed. So when you're in a low density medium, say in a warm white dwarf, the interaction between the absorbing atom, so say sodium in this case, and the perturbers, so helium in this case. So the interaction between both those particles will occur at large separations, and because it occurs at large separations, you can model the interaction potential with a simple van der Waals potential. And if you assume that they interact with the van der Waals potential, then you find the classic result that the line profile will have the same shape as a Lorentzian profile. But in cool white dwarfs, it's a bit more complicated because the interactions occur at smaller separations. And at smaller separations, you're probing a region of the interaction potential that can significantly differ from a simple van der Waals potential. So what you need to do is to compute this interaction potential for each in pairs that are relevant to your white dwarf atmosphere. And this interaction potential can be computed from ab initio calculations. And then from this ab initio potential, you can compute what is the real absorption profile for this particular interaction. And in some cases, it's very far from the simple Lorentz profile. So you can have a completely asymmetric line shape or even line profiles with local maxima in them. So here, when we did that and when I then implemented this in my atmosphere models, I found a much better fit once again to the observation. So you can see here the calcium feature is much better modeled, and of course this large sodium feature is also much better modeled. So this kind of improvement really matters because it now means that we can reliably extract the abundances of the planetesimal that was accreted by this white dwarf. And in this case, it turns out to be a very sodium-rich planetesimal, so it's a composition that does not look like any known solar system body. My third example is not a white dwarf that has accreted a planetesimal. So instead, this time it's a white dwarf that has dredged up carbon from its core. So that's why we see those molecular carbon bands. So this carbon was brought up to the photosphere by convective motions in the white dwarf envelope. So here the problem was that it was not taken into account that under high density conditions, it has been shown that the energy spectrum of the C2 molecule is distorted. And because you distort the energy spectrum, well, you also distort the shape of the absorption bands. But once we do take this into account, we can find once again a much better agreement with the observations. So I hope that those three illustrative examples convince you that the new atmosphere models do a much better job at reproducing the observed spectra of cool white dwarfs. Of course, my thesis does not only rely on those three examples. There are dozen more cases that we have studied, but I think they are good illustrative examples to show why it's important to have state-of-the-art physics in cool white dwarf atmosphere models. Now I should note, however, that there is still one class of cool white dwarfs that we have trouble with. So those are known as the ultra cool white dwarfs. So they are stars for which there are really strong absorption features in the infrared, and we still have trouble to reproduce those strong absorption features. So this is of course very annoying, but at the same time, ultra cool white dwarfs only form a small subset of all known cool white dwarfs. So there are still plenty applications that are possible with those new cool white dwarf atmosphere models. So I now have time to discuss two of those applications. So the first one concerns the spectral evolution of cool white dwarfs. So you might remember I said earlier that the spectral evolution of white dwarfs below 5,000 degrees is not well constrained. Well, the reason for that is that below 5,000 degrees, both helium and hydrogen stop showing spectral lines in the visible. And this is just because there is too little thermal energy to excite the atomic levels that are required to produce those transitions in the visible. So that's really annoying because we end up with completely flat, featureless spectra. And of course, from such a flat spectrum, it's very hard to tell if you're dealing with a helium atmosphere object or with a hydrogen atmosphere object. The only way we have around that is to look at the photometric observations. Depending on if you have a hydrogen atmosphere white dwarf or a helium atmosphere white dwarf, the continuum opacities are slightly different. So you end up with slightly different spectral energy distributions. So what you can do is that you can fit the observations using both hydrogen atmosphere models and helium atmosphere models, and then the best fit gives you the most likely composition for this object. So for example, here the black circles are a better fit than the white circles to the arrow bars. So this would likely be a hydrogen atmosphere object. Of course, this is very tricky to do. You can tell here that the differences between the hydrogen and helium models are very small. So we need to be careful with that. It's a very delicate exercise to determine the composition just by looking at the shape of the SED. So this approach has been used in the past 2 decades to look at the spectral evolution of white dwarfs cooler than 5,000 degrees. And vastly different conclusions have been found, ranging from a minority of cool white dwarfs having hydrogen-dominated atmosphere, all the way to almost all of them having hydrogen-dominated atmospheres. So the reason here for this disagreement is that because it's so tricky to determine the composition just by looking at the photometric observations, if you use a different atmosphere code with slightly different input physics, you can find a totally different answer. And this is an issue that really matters for white dwarf cosmochronology because hydrogen atmosphere objects cool down much slower than helium atmosphere object. So if you make an error on the composition of a cool featureless white dwarf, you could be making an error of the order of 1 billion years on its cooling time. So obviously this is something that matters. So previous studies that have looked into this problem had some limitations. So the first set of studies here were ignoring all white dwarfs that have metal pollution in their spectra, and we know well that a large fraction of cool white dwarfs have metal polluted spectra, so this is an important limitation. And the second set of studies here were relying on older atmosphere models that did not include most of the important non-ideal high density effects. So another important limitation. Now with my new atmosphere models, I can of course address both of those issues. And when I do so, I found that around 60% of white dwarfs cooler than 5,000 degrees have hydrogen-dominated white dwarfs. So the solution is basically between those two previous determinations. So now we still have to understand why we find this answer. So what are the physical phenomena that explain that there are 60% or so of white dwarfs cooler than 5,000 degrees that have a hydrogen-dominated atmosphere? But in the meantime, the main outcome of this research is that we can more reliably determine the composition of those white dwarfs' atmosphere, which means that we can more reliably determine the age of those very old white dwarfs. Then my second application concerns the composition of planetesimals accreted by white dwarfs. So quite recently, Hollands et al. Studied a large sample of some 200 metal polluted white dwarfs, and they looked at the composition of the individual elements that can be detected in those white dwarfs' atmospheres. So I'm showing here one of their important results. So it's the distribution in their sample of the magnesium to calcium abundance ratio. So the dominant feature here is that the peak of this distribution matches the magnesium to calcium abundance ratio of CI chondrites. And as I've explained earlier, this is not surprising because it would mean that the planetesimals accreted by those white dwarfs have on average a composition close to that of the average solar system. But there's a little twist here, and the twist is that the compositions that I'm showing here are actually the photospheric abundances, which are different of the planetesimal composition because of differential diffusion. So when you accrete magnesium and calcium in a white dwarf atmosphere, the calcium is expected to sink more rapidly than the magnesium below the white dwarf photosphere, which means that actually if your planetesimals do have a chondrite-like composition, then you should find a distribution that is shifted towards higher magnesium abundances. So what this result suggests is that there is a mechanism that can deplete magnesium in the planetesimals accreted by white dwarfs. So I decided to use my models to reanalyze the samples that was used to obtain this distribution. And I quickly found that there was a problem with previous models with the modeling of the magnesium triplet feature. So if I use now my new models to model this feature, I find a much better agreement with the observations. And it turns out that the magnesium to calcium abundance ratio that I find with those improved fits do lead to a distribution of magnesium to calcium abundances shifted towards higher magnesium abundances. So it becomes much more compatible with the idea that the material accreted by those white dwarfs was of a chondrite-like composition, and we do not need to invoke any magnesium depletion scenario. So to me, this is really a good example to explain why the work I've done in my thesis is important. It really shows that you need to have really state-of-the-art constitutive physics in white dwarf atmosphere models before we can hope to do any of those very cool applications. So let me do now, just before moving to the questions, a quick summary of my talk. So during my thesis, I used ab initio methods to improve the input physics of white dwarf atmosphere models. I then tested those new models for cool white dwarfs by comparing their predictions to actual observations. And in almost all cases, it works very well, except as I've mentioned for the ultra cool white dwarfs, which are still a puzzle that we have to solve. There are now many applications that are possible with those new improved and tested models. So we can measure more accurate ages for cool white dwarfs. We can look at their spectral evolution, and we can precisely determine the composition of the planetesimals that they have accreted. And of course, for cool white dwarfs, this means very ancient planetary systems, so planetary systems that are way older than our own solar system. So I'd like to thank everyone who was involved in this research. So in particular, my PhD advisor, Patrick Dufault, Nicole Allard for all our work on pressure broadening of spectral lines in white dwarfs, as well as Piotr Kowalski and Pierre Bergeron. On that, I think we have time for questions. Thank you so much for your attention, and I will just be letting my email address here in case you want to contact me afterwards. Thank you so much. Okay, so we now have a few questions in the chat. So first one is from Suza Oliveira Kepler. So can you talk a little more about the crystallization model and the carbon to oxygen ratio? Yeah, so that's an excellent question. So the carbon to oxygen ratio in the white dwarf core affects the exact temperature at which the core crystallization will take place. And it also affects the amount of gravitational energy that is released due to this sedimentation process of oxygen during crystallization. So it's quite a significant source of uncertainty in current white dwarf evolution models because it depends on what happened during the previous evolutionary stages. And there's still uncertainties surrounding that. So notably the nuclear reaction rates that are not all well known, and also the treatment of core boundary mixing during the core helium burning phase that precedes the white dwarf stage. So those are things that enter into the uncertainties regarding the carbon-oxygen ratio in white dwarf cores, and yes, this affects our modeling of core crystallization. Then I have a question from Regner Trempedak. So you mentioned density effects on atomic and molecular lines. Are there also density effects on continuum opacities? Yes, totally. The free opacities, the scattering opacities, they are all affected by the high density conditions, and it's important to take that into account. The reason I've not discussed that in this talk is that it's not as obvious as with the atomic lines and molecular bands to show the impact of the new opacities, just because they are continuum opacities. But yes, it's definitely something we need to care about under those conditions. Question from JJ Hermes. What do you make of the fact that the cool white dwarfs appear to have a lower mass than warmer objects? So here I guess JJ is referring to, let me find it, to this plot where we see that there are more low mass white dwarfs at low temperatures. So while this is really a puzzle to me and to everyone in the community, I think, I don't think it can only be explained by remaining problems in the atmosphere models, because it also affects hydrogen atmosphere objects, and hydrogen atmosphere objects are have much higher densities than helium atmosphere objects. So the physics is actually quite close to ideal gas physics. So there really should not be anything big that is still missing in our atmosphere models for those hydrogen-rich objects. So really, I don't know what's going on here. And yes, this is definitely something we have to look into. Thanks for this question. And then question from Harvey Richer. So convective coupling of the envelope with the white dwarf core occurs at the same time as core crystallization. So how do you distinguish between both of those effects? That's a really good question. So what Harvey is referring to here is that at some point in the evolution of the white dwarf, there is the convection zone really couples the core of the white dwarf, which is essentially isothermal. So it couples the core with the outermost layer of the white dwarfs, and after that the white dwarf can cool much more rapidly. So this leaves a signature on the white dwarf luminosity function, as does core crystallization. And for normal mass white dwarf, so for 0.6 solar mass white dwarf, this phenomenon occurs at the same time as core crystallization. So yes, it's very hard to distinguish between both effects. But now what's really interesting is that if you look at more massive white dwarfs, core crystallization actually occurs way before convective coupling. So say for a 1 solar mass white dwarf, maybe the core crystallization occurs at 12,000 kelvins and the convective coupling is only at 6,000 kelvins. So you can easily distinguish between both effects. That's actually the reason why it took us so long to really see the signature of core crystallization in white dwarf observations, is that you need to know the mass of the white dwarf to be able to say that it's really related to core crystallization. And we only had the mass of a large number of white dwarfs recently, thanks to Gaia parallaxes. So I hope this answers your question. So I think that's all the time we had. Thank you so much for your attention. It was a real pleasure to present this research to this diverse audience. Thank you so much and stay safe.